Alright, time for some more recursion, and now maybe you understand all of these fancy pictures a little bit more now. We stopped on Fibonacci, and I want to show you just quickly what is so cool about it. It is a sequence. We have come up with all these things. It starts at 0, then 1, then goes all the way. And you can make fun little spirals. The golden ratio, which this sequence approximates, just makes very pretty things. We think that beauty comes from the golden ratio. A lot of people believe that. So the golden ratio is this phi that you see here in all these equations. So yeah, please, I encourage you to read this Wikipedia page if you're interested. But let's go back to how we calculated this sequence. So we noticed that, oh, if we had a recursive case, fib5 is, well, that's just the two previous, fib3 plus fib of 4. That looks like a recursive case to me. So fib of n is fib of n minus 2 plus fib of n minus 1. And we needed two base cases because we couldn't be like, fib of 0 is 0, but fib of 1, that's not 0 plus fib of 0 plus fib of negative 1. No, we have to have a second base case for that one, so that then the recursive case starts here, and it's like, oh yes, it's 1 plus 0. Fib of 1 plus fib of 0. Okay, yeah, let's keep those maybe. How many circles did I draw? Sure. Okay, so let's code this, and then let me tell you why it's really super slow as well. Okay, so fib.cpp, just a bunch of functions this class. Let's see here. It'll be like cout fib of, what was the last one I wrote? 5? How about 6 then? 6 should be 8. So int fib int n, supposed to return the nth Fibonacci number. In the sequence. So if we have two base cases, if we're trying to find 0 or 1, the answer is 0 and 1. Yeah. And a slick way of writing that is if n is equal to 0 or n is equal to 1, return n. Isn't that cute? Otherwise, we're in the recursive case, and we'll be like, all right, we'll return fib of n minus 2 plus fib of n minus 1, because in that case we know that there's at least 2 before us that we can use to calculate. Okay. So then fib of 6, in theory, should be 8, and let's watch it work. Beautiful. And hopefully it makes sense, this kind of thought process again. It's like, okay, let's pretend that fib works for smaller numbers. Let's use that fact, use that concept to just build up the proper answer using the assumption that these are working. Okay, so just assume that fib of smaller numbers, smaller n's, works perfectly. Use that to build up the bigger solution. This is just the coolest thing. As long as the base case is correct and your use of the recursive case is correct, you will have built up the proper answer, because it'll go down to the base case and then correctly build itself up. I'm going to keep repeating that it's the weirdest thing, but it works. Okay? And I want to show you why this unfortunately is a very, very bad implementation of this. And let me tell you why. We're repeating so much work. And here is the reason. If I call, let's be nice to ourselves. How about, let's say fib of 4? Let's say we originally wanted to calculate fib of 4. That's going to call, because it's going to hit the recursive case. Oops. It's going to call fib of n minus 2 and fib of n minus 1, eventually. It'll call one first and then the other. But eventually it's going to make these calls. Fib of 4 minus 2 is 2, fib of 4 minus 1 is 3. And then this fib of 2 is going to call fib of 1 and fib of 0. Fib of 0. And fib of 3 is going to call fib of... No, I guess I did it backwards, sorry. It's going to call fib of 1 and fib of 2. And then fib of 2 is going to call fib of 1 and fib of 0. But again, I did it backwards. Fib of 0, then fib of 1. The order doesn't really matter. Just the idea is, look at how many times I'm calling fib of 0. 1, 2, these are separate calls. Look at how many times I'm calling fib of 1. Fib of 2. Need to dot it. Used some dots there. And then, oh no, what if I was calling fib of 5? Oh, sorry. Well, then we'd have this, and then we'd also have fib of 3, which is just this whole thing all over again. Oh, shoot. So much repetition. You can see how many times we call fib of 0, fib of 1. It's going to be a lot. It increases exponentially, we say. And so, this case, it's easier to do the iterative version. There's a way to solve this problem, but that's a more advanced topic. Until an algorithms class, I guess. That's when you'll learn about this. How to solve these problems recursively, but fast still. And so, because it's repeating all this work and it's doing all this silly stuff so many times, it'll just never finish sometimes. Like, you try to call fib of 200. This will never finish because of all the repetition. And I'm just going to wait until the end of time. That's no fun. Okay, so we might talk about this a bit more, like in CSCI 41. You'll see more about this, definitely. But that's where I want to leave you right now. So that's Fibonacci. Let's go back. Let's do something that's not calculation. Let's write a function that's like print from 1 to, and then int n returns just a void function. Let's write this one. Print from 1 to n in order. Okay, so that's our function. That's its declaration. How are we going to print from 1 to n in order? So again, let's use an example and figure out where the recursion can help us. Like where is the recursive call? So if we want to print, let's say we want to do our problem at 5. Let's go back to blue. Let's print from 1 to 5 in order. So we want the final output to be 1, 2, 3, 4, 5 in that order. Can you pause the video and find a smaller printing from 1 to n in order problem inside of this one? Because that's all that recursion is. It comes down to this. Can you find a smaller print from 1 to n problem? And I think you'll notice P of 4 right there. So, oh shoot, that's our recursive case. Just solve recursively, print from 1 to n minus 1. You see that? To one smaller, and then print your n in that order. Because first you have to recursively solve the smaller problem, and then you print your 5, your original bigger number, your n. Okay? So that's your recursive case, and I hope this is getting slightly less confusing. Like, it's hurting your brain slightly less now. I understand that it's going to take a while to sink in. The base case is when do you stop? It's like, okay, this is P of 4, here's P of 3, here's P of 2, here's P of 1. Like, how do you print from 0? What's P of 0? How do you print from 1 to 0 in order? There's nothing to print, right? So, how about that? There are no numbers between 1 and 0 in order. Too small. So just print nothing. Nothing. Okay. And that's actually the answer. So again, let me code it up. Print stuff.cbp. Print from 1 to 5. And we'll code it up as well. So it's a void function. It just prints, and it takes an int what you want to print up to. So in order, here's what we do. Check our base case, because we always should check that first so that we don't accidentally do the recursive case too many times. So if n is 0, do nothing. Return. Do nothing. Base case. Else, well, what are we going to do? We're going to recursively print from 1 to n minus 1. We get to assume that that works. Just assume that it's going to print 1 to 4 for us. It's our job to build up the final answer, and if we build it up correctly, it will be correct. I know that's weird, but it is mathematically precise. It does work. So we say print from 1 to n minus 1. Just assume that this works. Now, our job is to solve the bigger problem by printing our n next. So if we printed from 1 to 4, we need to add our 5 because n was 5. Okay? So let's do this. 1, 2, 3, 4, 5. Let me draw the stack again, just to give you an idea of why this is working. Lots of diagrams this lecture. So for main, we're like, please print from 1 to 5. So I'll say p of 5. And we hit the recursive case, of course, because it's not 0, it's 5. So we're going to first recursively print from 1 to 4. And then we'll worry about printing our 5. But first, we have to get this call to work. We have to run p of 4 before we can see out our 5. So p of 4 gets called, and then p of 5 is waiting for that to finish. Okay. Similarly, p of 4 is like, okay, to print from 1 to 4, I'll first print from 1 to 3. Then I'll print my 4. P of 3 is like, oh yes, I'll first print from 1 to 2, then I'll print my 3. Hopefully this is making sense. And p of 2 is like, okay, I'll print my 1 to 1 first, and then I'll print the 2. P of 1 is like, okay, yes, I'll first print from 1 to 0, and then I'll print my 1. This one does nothing. This one causes no output, so it just returns, it's done. We have outputted nothing so far. This is like our screen. Then P of 1 is like, okay, I was waiting for P of 0 to do its thing. It did its thing. And I'll print my 1 now. Print my n. So everybody's waiting to print their n at this point. P of 1's like, okay, yes, print my 1 now. Because I was waiting for P of 0. P of 2 is waiting for P of 1. It's done. It printed from 1 to 1. So you can see it was correct. P of 2 is going to now print its 2. That solves its problem. P of 3 was waiting for P of 2 so it could solve its bigger problem, printing from 1 to 3. So it first printed from 1 to 2. Now it'll print its 3 to solve its bigger problem. Then P of 4 was waiting to print from 1 to 3, and now it's going to print its 4. P of 5 is waiting on P of 4 to print from 1 to 4. Now it'll print its 5 to solve its bigger problem. And now we're back in main and we have the correct output. Okay? Hopefully it's sinking in. Now let's do the same thing, but in reverse order. So instead of, I definitely think that drawing an example is always useful. Instead of P of 5 now printing 1 to 5, it's going to print 5 to 1. So where's the recursive case? Where is the smaller print from 1 to n in reverse order? I guess let's say n to 1. Where's the smaller one? I think you see it's here. That's P of 4. So in our recursive case, what's the order? What's the order of things? Eventually we're going to say recursively print from 4 to 1, but where do we print our 5? where does the 5 go? It goes before this recursive call. The 5 needs to appear before the 4, 3, 2, 1. You see that? You see how the order is very important? Print n. And then we'll print recursively from n minus 1 to 1. That's the recursive call. Then the base case is, again, it can do the same thing. It's like, okay, p of 3, p of 2, p of 1, p of 0 is, again, do nothing. So watch this. Print reverse, let's say. Let's give ourselves some space. Print reverse from 1 to that. So print reverse from 1 to 5, so print from 5 to 1. Let's just say print n to 1. I would rather call it that. There. So, base case do nothing. Recursive case, look what happens. We need to print ourselves first, then we make the recursive call. This is n minus 1 to 1. This is print n to 1. Notice that this is exactly the same except the 2 lines in the recursive case are swapped. Look at these 2 functions. They're the same. They're exactly the same except for where you print the n, and that makes all the difference. Isn't that weird? This'll work. It'll do it reverse because you print the n first. You see that? Crazy, but this is why. Just assume that it's going to print from 4 to 1. Print our 5. The 5 has to come first because we want to print from 5, 4, 3, 2, 1. Okay, it all makes sense, and it's going to lead you to the right answer. That assumption, but it's kind of cool to think about how it's kind of the same function. These two. It's just the order of that recursive case's body. Yeah. Beautiful, and I encourage you to draw the stack for all of these. Okay, some more examples. Print the characters of a string in order. This will be fun. Well, let's say I want to print, I don't know, I have like hello. That's my string. So I want to print H, then E, then L, then L, then O in that order, but I want to do it recursively. So can you find me a smaller print a string problem inside of this output? That's P of hello. I think you can. Well, you can find like P of hell, P of LO, P of L, but the way that we want to think about it as computer scientists is usually get rid of the first thing and then work on the rest. But you could totally do it backwards. You could be like, that could be your smaller thing. Totally fine. But I'm going to call this one our smaller case. P of LO. That could be our recursive call. Okay, so recursively. Well, let's work on the base case first. That one's easy. When do you not have to find a smaller string to print? That, I think, is when the string is empty. So in the recursive base case, in the base case of this recursive function, if the string is empty, print do nothing. print nothing, do nothing. Okay, in the recursive case, print your first character. This is how we're going to do it. Print your first character. It's kind of like this print in reverse. Print the first character, and then print the smaller string recursively. Okay, do you see how I found the smaller problem inside of itself? That's key. All right, is this still working? Yeah. Okay. I'll just keep it in this file, I guess. So we'll say void print chars of string s, and of course I'm going to need to include the string library now. So let's do it like this. Base case, s is empty. Just return do nothing. Else, print your first character. And then recursively print the smaller string. Now I just want to highlight the fact that you can break this down in a different way. There are multiple valid recursive cases. I'm just showing you one way. Another one is you pop off the last character. So this could be your smaller problem. Okay. So how do you do that? You say print. Well, I guess we have to make the smaller string. String smaller string. Well, it's not s, but it's s with some stuff removed, right? So we're going to have to say s dot erase. And let's see here. At position 0, please erase one character. How about that? And I think then we can call print chars of string with smaller string. Yeah. Let's see if that works with printing hello. Oops. Hey. Oh, and I forgot the new line. Excuse me. But it looks like it's working. Beautiful. All right. So that is that. We have just completed this problem of printing the smaller string, which we consider to be everything but the first character. Okay, so that's that. And now let's do the same thing, but let's do it in reverse. Okay. So, and I think the erase function actually just edits the original string, so I just probably could have called s erase 01. But it's nice to do this, I think. It looks a bit cleaner. So, let's make this work. How are we going to print it in reverse order now? So let's pretend again we're trying to solve p of hello. And we want to print OLLEH now. So where is the printing reverse smaller subproblem? Can you find me that? And if you stare long enough, hey, here's the reversed printing of LO. Isn't it? So there it is. So in the recursive case, it's just recursively print the smaller string backwards first, because that needs to appear before the H. Recursively print the first character. Okay. And let me use strings properly this time. And I'm going to have to save the original string. There we go. Now it's saved. Now I can erase from it, recursively print the smaller string in reverse, and then print the first character of the original string. Okay, I guess we'll have to call that. And again, it's just the idea of making the recursive call first now kind of does things backwards. I really encourage you to draw the stack to get a better feel for why it's doing it. But again, you can just assume that the smaller call, the smaller recursive call, does the right thing as long as you build up the answer correctly. We need to put the H in the right spot in that order. Okay? Base case stays the same. Okay, I got two more normal examples for you. So another one is kind of something that you'd normally do with a loop. So capitalizing a C string. So if I had the string hello again, if it was a C string, it would look like this, right? Those are all the characters. And I want to transform it into capital H, capital E, L, L, O. And obviously keep the null terminator character because that's what it needs to still be a C string. Okay, how shall we do this? So we need to find a smaller capitalization problem. Okay, so it's like if this is P of stir, P of the string hello, is supposed to calculate this, where is the smaller capitalization problem? Again, they're usually always in the same spot. This is why I'm showing you multiple examples. They're kind of always in the same spot. Here is the capitalization of a smaller string, a smaller C string. And the key is you cannot break it down in the opposite way. This cannot be your smaller string because it's no longer a C string. You forgot about the null terminator character. So you have to break it down this way, in fact. So that can be our recursive case. We will capitalize, it doesn't really matter the order, capitalize the start of the string, work on our H, make it a capital H. Then we'll recursively capitalize the rest of the string. Excluding the first character. Okay, you could technically do these in either order. Doesn't really matter, because you're just changing things now. And then the base case, what do you think is a string that doesn't need to have a smaller string capitalized? Well, that's just the empty C string. So once you get to that, you can stop, right? Capitalize this one, this one, this one, and this one doesn't need to be capitalized. See that? There, that's prettier. Okay, so let me, I guess I'll need a new file. This isn't about printing things anymore, is it? Capitalize C string.cbp. So let's have our favorite C string, I don't know, stir equals hello, just like that. And we'll say capitalize stir, and then we'll print it out. Okay, so capitalize is a void function, just does something, but it's recursive. Char star s, that's our string. So how are we going to do this? This gets interesting. The way that you call it is interesting. This is very similar to something else that we've already done, but the way that we write code for this, I think, is interesting, so that's why I'm giving it as an example. So, okay. We first need to figure out if we're in the base case or not. So figure out if we're in the base case. So if this is the empty string, do nothing. Oops, nothing. And how do you check if it's an empty string? You can't say s equal to empty string. That doesn't work. This is a C string after all. It's just a memory address. So we can say strlen. That would work. Or we could check if the first character was the null character. We can say strlen s. If that's 0, alternatively, this would work. We'd say if s of 0 is equal to the null terminator character. So it's the end of the string already. Return. Else. I guess you don't really need an else case for all of these because you've already returned. So otherwise, if we're still here, we're in the recursive case. And so we'll capitalize the string, capitalize the first character, and then we'll recursively capitalize the rest. So it's easy to do this one. S of 0, it's whatever it was, but 2 upper. And then recursively capitalizing the string is the hard part. What's the call that we make? Capitalize. How do we give it the smaller string? What goes here? So that's where we need to talk about indices, pointers again. So the string, remember that the string is secretly a pointer. It's like a pointer to the first element, the first index. It's like if this was address 100, this was like address 101, 102, 103, 104, 105. Sorry. And the string is represented as a pointer to the first character of it. So the next string, the string after it with one less character, is s plus 1. Or stir plus 1. Just for consistency's sake, this is now s. It'll give me the smaller string because it'll start pointing to, not here, it'll point to 1 after it, the next address. That's the string now, okay? Because the string is represented as a pointer to its first character. So the smaller string looks like this, s plus 1. S plus 1 is the address of the next character in S. And remember, because strings are represented as a pointer to the start of it, this correctly gives the passes along the smaller string. Okay, it's weird, but it works. And so we've got a recursive case. We're recursively capitalizing the smaller string. We're solving the problem inside of itself on a smaller version. We've got a base case, and everything looks correct. Let's compile and run. Yes, hello, it's yelling at us. I love this. So even though it's just like the hardest topic in this class, it's my favorite. Okay, the last real example I want to give you is scrambling the characters of a word. This is something that you'll read about in your book as well, but I want to give you just another way to do it as well. So I want to get you to think about it in a certain way. So let's pretend we have just a normal string like S. We have like hello, and we want to print out every single way that we could scramble those characters. So we really want to find all the permutations of the characters of a word and print them out. So if I gave you cat, What's P of cat? Well, that should print. This is going to be fun for me. Well, cat is a possibility. CTA is a possibility. Then let's see, ACT, ATC. Then we have T, AC, TCA. I think that's it, because it's 3 factorial that is 6, right? So we've got 6 possibilities. Every permutation. Okay, how in the world are we going to recursively do anything with this? Where is the smaller scrambling of words problem inside of this? Actually, let's not print them out. Let's just generate them and like make a vector of all of them. So how do we make a vector of all this stuff recursively? Where's the smaller word scrambling problem? And I think you might be able to find it. The way that I wrote it out is kind of indicative of what I was thinking. Notice that you can think about this problem as pick the first character. Like, just decide on a first character. And then find all the ways to scramble the rest. Do you see that? This is definitely not obvious and not intuitive. But if you stare at it long enough, that is the idea. Okay, so it's like pick your starting character, pick a starting character, and then scramble the rest of the characters that are left. Okay? So, pick a starting character. Scramble the characters that are left. There aren't as many of those smaller characters. That's a smaller problem. Beautiful. Okay, so for this, we're like, okay, I picked C. That's my first possibility. So I'm going to randomly scramble AT and TA. I'm going to randomly scramble A and T, giving back all the ways I could have done that. I'm going to randomly scramble CT and TC, give me back all the ways I could have done that. I'm going to randomly scramble AC and CA, give me back all the ways that I could have done it. Okay, so that's the idea. What's the base case? When is there only one way to scramble something? When is there nothing to scramble? Those are 2 valid base cases. One of them is empty string. Do nothing. Again. Do nothing in the empty string case because you've scrambled all the 0 characters. The recursive case is the weird one. So pick a starting character. You have to try them all, though. And then recursively, scramble the remaining characters. Okay, and then put your character that you picked at the front. So build up the vector consisting of all of those things. So that's a lot of words. It might not be too intuitive either, but let's code it up together and it might make some more sense. So let's do this. Let's say int main, let's scramble. That cat still works. And it's going to give us a vector of strings, all the different ways we could have scrambled. Scramble cat for me, please. And then let's print out all the possibilities. Alright, so our idea is we need to, I guess I also need to include vector. We gotta make a function called scramble, and it returns a vector of strings, and it's taking a string s. Alright, so we need to build up a result vector and somehow work with that. So this will be our result vector. So, base case. That's the easy one. When there's nothing to scramble, we have an empty string. So let's do nothing. If s is equal to the empty string, return res. Res is empty right now. We give back an empty vector. Otherwise, we're in the recursive case. If we're still in this function, we're in the recursive case now because we didn't return. Okay, we need to pick a starting character. So we've got as many of the string to try. We gotta try the C, gotta try the A, gotta try the T. Let's try them all. For char starting character equals, oh sorry, let's do int I equals 0, I is less than s dot size I plus plus. So char starting char equals s dot at I. So that's the character we're gonna pick to start. It'll either be C or A or T in this case. Okay, so now we have the starting character. How do we get the rest of the string? Oops. How do we find the AT, the TA, the CT, the AC? How do we get the fact that, oh, if we took the C, we have A and T left? Where's the string with the rest of the characters? You can do this with some fancy subster calls, but I'm not that cool to do that while I'm thinking and talking, so I'll do it the easier way. Your book will show you the harder way. Start out empty, and just be like, all right, for int I equals 0, I is less than s dot size, I plus plus. Oh, this is the other string. Let's call it rest. We'll be like, okay, oh, I'm so sorry. This should be J. Okay, so these are all J's now. If J is not equal to I, so it's not the one that we chose, add it to rest. That's the idea. There's your the rest of the strings that you want to, the rest of the characters that you want to scramble. Okay, so we'll say rest plus equals s dot at J. So this, if I was 0, this would get rid of the C and only add the A and the T. So it would make me a string with just A and T in it. And that's what we wanted. That was the rest of the characters in the string rest. Okay, so let's scramble those. We'll get back a vector. Equals scramble rest. We're recursively scrambling the rest to get our AT and TA in this case. If we pick the A, we'd get our CT and TC, a vector of strings. Bear with me. And then we need to go and add our starting character to the start of every string there. Because that was our goal. It's like, okay, you gave me back AT and TA, I'm going to put my C in front of that. You gave me back CT and TC, I'm going to put my A in front of that. Okay? So, let's do this. For string reference, because we want to change it, s in scrambled rest. No. Let's call it stir, maybe. Scrambled rest. Stir equals mark our first character, starting char, plus stir. Okay, so now we've changed them. We've added that character to all of them. And so now I have a vector with just cat and CTA. Now I have a vector with ACT and ATC. Now I have a vector with TAC and TCA. Add them all to my result vector. So I don't know if there's a way to like say plus for vectors, so let's just go through and push back everything. So for string stir in scrambled rest res, that's what we called it, right? If we go back, yeah, we called it res dot pushback. So build up our result vector, and then finally, I think we're done. Return res. So either way, we're returning res, which is funny. It's just the recursive case is kind of a pain. Pick a starting character, find the rest of the characters, that wasn't that one, so that we can scramble them, recursively scramble them. We can assume that that's going to work. Then add our starting character back to every result that we got back. We're getting vectors. And then finally, we've got all our scrambled strings to add to our result vector. And we're going to try this for every starting character, and so we're going to get every possibility. Okay, that's kind of hand-wavy, but hopefully it kind of makes sense. You're going to read about this in great detail in your book, so just wait until then, maybe. And did I call anything? Scramble cat, and I compiled this into scramble./scramble. It would appear that I have a bug somewhere, so I'll look for that. Okay, I've noticed my error. It's not do nothing for the base case, because I thought we were printing still. My fault. It's return just one possibility, return a vector containing the empty string. Otherwise, we never give back a vector with anything inside of it. That was the problem. So we all make mistakes. So we're not returning res empty. We need to put the empty string. And return it. So res.pushback, the empty string, then return res. So we're going to return a vector with just the empty string in it, because that's all the ways that you can scramble the empty string. That was incorrect. Now, it finally works. So the recursive case was correct. I accidentally put the base case as the wrong thing. Okay, so that's why both go hand in hand. Got cat, CTA, ACT, ATC, TCA, TAC. All right, and you can try this with much longer things, and of course this blows up because I don't know what's a very long word. Scramble. Let's scramble the word scramble. Boop. That's a lot. And if there's any repeated letters, there's going to be repeated ones of these. So let's go back to maybe cat for now. So that's that, and the last thing that I want to tell you about is this thing called the Tower of Hanoi, which maybe you've heard about it, maybe you haven't. It's just a fun example of recursion that I don't expect you to understand. It's just something everybody knows or learns about, at least in words. So I'm going to show you what's going on in words. So the idea of this game is you want to move all of these things to this peg over here. Move this entire stack to this peg. But the game is you can only put smaller pegs on top of smaller pegs. So you can't put that one here and then put the one that was now on top over here. You can't put that one on top. They have to be in increasing order. Okay? So that one would be forced to go over here. Something like that. And the name of the game is you have to do a lot of moves to move a large stack with those rules. So the base case is you can solve this with recursion quite easily, in fact. Even though there's like a million moves you have to do for a large stack. Doesn't matter. For the base case, it's you can move the smallest disk wherever you want. It's like it can go wherever you want because it's always going to be the smallest. It can always fit on top. And then the recursive case is the weird thing. It's you recursively move the one smaller stack. So this is your sub problem. Move this smaller stack except for the last one. recursively move that right here. Okay? Move it to this intermediate peg. And you can use this one as your intermediate peg, but this is the destination for the smaller stack. And then finally, you'll have moved all that here, and you'll have this last peg, which you can then finally move to where you want it to go. So just in one line, move the biggest disk to the destination. And then recursively, you got the big disk here and you got the smaller stack here now. Recursively move all that right here, using this peg that's now empty as the intermediate. So if that made no sense at all, don't worry. I'd be happy to talk about it more in office hours. It's just a fun little example that you might see in your book or just on the internet, because it's a common one when you learn about recursion. So that's the Tower of Hanoi, and now let's get you out of here. So some things that you can do to improve your knowledge of recursion is realize that anything you can do with a loop, you can do with recursion. So you technically don't need a loop in C++. You can just do everything with a recursive function, or a combination of them. And some things are easier to think about with recursion. Like this problem in particular is very hard to think about iteratively. And so the best exercise I can give you is go back to the examples that I used when I was first teaching you loops, like while and for loops. Convert every one of those, because they all can be. Convert as many as you can to be recursive functions that calculate the result or perform the operation that it was trying to perform. All of those things, I'd be happy to talk about them with you or help you. Just notice that recursion is just as expressive as loops. No more, no less. So that's where I want to leave you. You are now probably thoroughly confused. This is a very difficult concept, so thank you for getting through it with me. You're going to have some examples in your lab now to hopefully drive it home some more. So I'll see you there.